Welcome to ReneEnergy.com on YouTube, the hub for all things renewable energy and sustainability. Our channel is dedicated to bringing you the latest innovations and insights in green energy, including cutting-edge developments like green hydrogen. Whether you're a sustainability veteran or just beginning your journey, we have something for everyone. Join us on this channel to explore inspiring projects for a sustainable tomorrow. We bring you the latest in renewable energy, sustainability, and cutting-edge technologies. And don't forget, for more in-depth information and resources, visit our website and subscribe to our newsletter for the latest updates and exclusive content.
Welcome to our in-depth exploration of the inner workings and supply chain dynamics of PEM Electrolysers. In this presentation, we will take you on a journey into the heart of this innovative technology, describing in detail how each component contributes to the overall performance of the system, while also examining the complex network of vendors and suppliers that make it all possible. A PEM electrolyzer, or proton exchange membrane electrolyzer, is at the forefront of clean hydrogen production, a key technology for a sustainable energy future. Its design revolves around the ability to split water into hydrogen and oxygen, using an ion-conducting polymer membrane that not only facilitates the movement of protons, but also maintains the separation of the resulting gases, ensuring that they do not recombine. At the center of the system lies the Membrane Electrode Assembly, a sophisticated integration of multiple layers, each engineered for a specific function. The proton exchange membrane itself is a critical element, often composed of a material like naphthen, which has become the industry standard. This thin, ion-conducting polymer is essential because it allows protons generated at the anode to move to the cathode, while keeping electrons confined to an external circuit. This separation is crucial for achieving the electrochemical reactions necessary for water splitting. Alongside the membrane are the catalyst layers. On the anode side, catalysts such as iridium oxide facilitate the oxidation of water, breaking it down into oxygen, electrons, and protons. On the cathode side, catalysts, typically platinum-based, are responsible for reducing the protons to form hydrogen gas. These catalysts are carefully deposited onto the electrodes to maximize the reaction surface and efficiency. Complementing these active layers are the gas diffusion layers, which serve the dual purpose of evenly distributing water across the active surface and removing the produced gases from the reaction sites. The design of these layers is optimized to enhance the overall performance of the electrolyzer by ensuring that there are no bottlenecks in reactant delivery or product removal. Beneath this core assembly lies a network of additional components that together form a complex and finely tuned machine. The bipolar plates, for example, serve as both electrical current collectors and structural supports. They incorporate intricate flow fields that channel water to the reaction sites, while simultaneously directing the produced gases away from the electrodes. These plates are often manufactured from corrosion-resistant materials such as titanium or advanced composites, ensuring longevity and durability in the harsh operating conditions of an electrolyzer. The entire system operates under the principle of water electrolysis, where water is fed into the anode compartment and split into its constituent parts. At the anode, water molecules undergo oxidation to form oxygen gas, protons, and electrons. The protons then traverse the membrane to the cathode, where they combine with electrons arriving from the external circuit to form hydrogen gas. This simple yet powerful reaction is the cornerstone of clean hydrogen production and is what drives the growing interest in PEM electrolyzers as a sustainable energy solution. Behind this remarkable technology is an equally intricate supply chain that brings together a diverse array of vendors and suppliers. The production of high-performance proton exchange membranes, for example, is dominated by a few key players such as Chemours, whose naphthen material is widely recognized for its efficiency and reliability. This concentration of supply ensures high quality and performance, but also introduces a level of risk, as any disruption in the supply of these critical materials could have a significant impact on the overall market. To mitigate such risks, the industry is actively exploring alternative materials and innovative manufacturing techniques that could diversify the supplier base and reduce dependency on a single source. Similarly, the catalyst layers that drive the essential electrochemical reactions are supplied by well-established companies like Matthey, BASF, and Heraeus. These organizations specialize in the production of high-quality catalysts that rely on precious metals such as iridium and platinum. While these materials are chosen for their superior catalytic properties, their scarcity and high cost pose significant challenges for scaling up production. In response, research and development efforts are increasingly focused on reducing precious metal loadings and discovering alternative catalysts that can deliver similar performance at a lower cost. In addition to these primary components, other parts of the electrolyzer, such as the gas diffusion layers and bipolar plates, are provided by companies with expertise in advanced materials. For example, firms like SGL Carbon and Toray Industries lead the market in producing high-performance gas diffusion layers that are engineered to deliver consistent performance and enhanced durability. The manufacturing of bipolar plates often involves a combination of in-house production and collaboration with specialized suppliers. This dual approach allows manufacturers to optimize the design and performance of the plates, while also ensuring that the materials used are of the highest quality. Beyond these core components, the supply chain extends to a range of ancillary parts, including seals, gaskets, sensors, and electrical connectors. These elements are typically sourced from a broad pool of industrial suppliers and are standardized across many applications, which helps to keep costs in check and reduces the complexity of the procurement process. The convergence of advanced technology and a highly specialized supply chain has far-reaching implications for both performance and scalability. On one hand, the use of sophisticated materials and precision-engineered components enables PEM electrolysers to operate at high efficiencies, making them ideal for large-scale hydrogen production. On the other hand, the reliance on rare and expensive materials such as iridium and platinum introduces vulnerabilities in the supply chain, making it imperative for the industry to innovate continuously and explore alternative materials. Manufacturers are increasingly adopting strategies such as vertical integration and long-term supplier partnerships to mitigate these risks and maintain a competitive edge. This approach not only enhances the stability of the supply chain, but also allows for tighter control over quality and cost, ultimately driving down the overall expense of hydrogen production. The challenges associated with material costs and supply chain vulnerabilities are also spurring significant research and development initiatives. Across the industry, there is a concerted effort to develop new materials and technologies that can replace or reduce the dependency on scarce resources. Innovations in membrane technology, for instance, are aimed at improving ion conductivity while simultaneously reducing manufacturing costs. Similarly, breakthroughs in catalyst design seek to achieve the desired electrochemical performance with lower loadings of precious metals. These efforts are not only technical in nature but also strategic, as they involve close collaboration between research institutions, component manufacturers, and electrolyser OEMs. The ultimate goal is to create a more resilient and cost-effective supply chain that can support the rapid expansion of hydrogen production, thereby accelerating the transition to a cleaner, more sustainable energy system. As the global demand for clean energy continues to rise, the potential for PEM electrolysers is set to expand dramatically. The increasing focus on reducing carbon emissions and transitioning to renewable energy sources has brought hydrogen to the forefront as a viable energy carrier. In this context, the technology behind PEM electrolysers represents both a technical marvel and a strategic asset for the future. The intricate interplay between the internal components and the global supply chain underscores the importance of innovation, collaboration, and strategic planning in this rapidly evolving market. By addressing the challenges posed by material scarcity and supply chain concentration, the industry is poised to unlock new levels of efficiency and scalability, paving the way for a more sustainable energy landscape. The economic and environmental benefits of PEM electrolysis are becoming increasingly clear, and this technology is gaining momentum as a critical component of the global energy transition. With the rising cost of fossil fuels and growing concerns about climate change, hydrogen produced through electrolysis offers a cleaner alternative for a wide range of applications, from industrial processes to transportation. However, realizing the full potential of this technology requires not only advances in engineering, but also the development of a robust and resilient supply chain. By fostering innovation and building strategic partnerships, the industry is working to overcome the challenges posed by limited material availability and high production costs, ultimately paving the way for a scalable and sustainable hydrogen economy. Throughout this journey into the realm of PEM electrolysers, we have seen how the convergence of advanced materials, precision engineering, and strategic supply chain management creates a powerful platform for clean energy production. The story of PEM electrolysis is one of continuous innovation, driven by the urgent need to transition to more sustainable energy sources, while overcoming the practical challenges of material scarcity and high costs. As the industry continues to evolve, the lessons learned from these efforts will not only benefit hydrogen production, but will also serve as a model for other emerging technologies in the renewable energy sector. The path forward is one of collaboration and strategic foresight, where every component, every supplier, and every innovation plays a vital role in shaping a sustainable future. In closing, The exploration of PEM electrolysers reveals a multifaceted narrative that intertwines cutting-edge technology with a global network of suppliers and strategic partnerships. It is a story that encapsulates the challenges and triumphs of modern engineering, offering a glimpse into the future of clean energy production. Thank you for joining us on this detailed journey into the inner workings and supply chain intricacies of PEM electrolysers, a technology that is not only transforming how we produce hydrogen, but also reshaping the landscape of renewable energy for generations to come.
Thanks for tuning into the ReneEnergy.com YouTube channel. We trust you found this episode enlightening and motivating. There's a world of innovation and opportunity in sustainable energy, and we're delighted to share this journey with you. Stay in the loop with the latest on renewable energy and sustainability by visiting our website and subscribing to our newsletter. Your support is immensely appreciated, it's truly invaluable to us. Don't miss our next video on new trends in renewable energy. Follow us on social media for the latest updates. Enjoyed the video? Like, subscribe, and share for more green insights. Thanks for watching.